last two classes we have read how to design the synchronous sequential design. Now today we will read the finite state machine design. Again, that is a sequential machine and synchronous sequential machine. Before that, we quickly see the answers of the lecture 23 quiz. Now the questions were, which flip flop yields lowest gate counts? And as already we have read JK flip flops, D flip flops, RS flip flops, and we have seen that JK flip flops yield lowest gate count. Now which flip flop yields best literal counts? The most popular, the D flip flops yield lowest literal count. And which flip flop is best suited for VLSI implementation? Again, D flip flop is best suited for VLSI implementation, as already we have seen that this is very impact and simple to design. So today we will start the finite state machine design. We start with an example. Say example is odd parity checker. All of we know parity means, say in a string of zeros and ones, if the total number of ones is even, that means number of or XORs of all ones become 0, then it is a even parity, and if the number of ones are odd, then it is a odd parity. Now the parity checker here we are seeing that is the odd parity checker. So indicate whenever input bit stream has an odd number of ones, that means it will generate a one output whenever odd number of ones exist in the input. So if we represent the state transition table or state diagram, last day we have learned, then if the present state is even and the input has come as a 0, then the next state is also even and output is a 0. Now if the present state is even and one input 1 is arrives, that means next state will be odd, because earlier the present state was even, now input has reached 1. So next state is odd, and the output is, if we consider the present state, just the present output, this will be a 1, and if we want this 1 we stored, and in the next clock cycle we want to generate this as the output, then actually in the next clock cycle this 1 will be give as a output. Similarly, that if present state is odd and one input 0 has come, obviously next state is odd because input 0 arrives, then also one output is there. So this is again one output, and in the next clock cycle it will be taken as the output. So actually even present state input 1 will generate output, and odd present state input 0, that will be generating one output, and in the next clock cycle that will be shown as the output. That is why the outputs are shown here instead of output is shown here instead of in these places. So the state transition table means that with respect to the 0 and 1. Now if we denote the even state as 0, that means here there can be two states, even and odd. So, I need only one bit to represent the state, and that even means I am telling 0 and odd means I am giving 1. So, this is called the state encoding. So, if my already we have seen that actually this is even. So, if the present state is even and input is 0, next state is 0, output is 0. If the present state is even, that means 0, input is 1, it give next state is 1, because next state is a odd state, odd is 1, and output is 1, that is shown in the next clock cycle. This is the next clock cycle. Similarly, the odd state is encoded as 1. So, present state is odd, input 0, then the next state is 1 and again 1 output. Next clock cycle it will be shown in the output line. Then again odd present state, input 1, next state is 0, output is 0. So, this is the state in transition table with the state encoded as 0 and 1. So, if we represent that as a state diagram, again there are two states. So, this is my even state means 0, this is my odd state that is encoded as 1. Now, if it is a, that means reset means always when it start, when the machine starts, the machine starts, the starting state will be 0. 0 is the starting state or initial state. Now, if a if a 0 input arrives, so this is a 0 and the it will next state will be even. So, it lies in the same state. Now, if a 1 input arrives, then even state input is 1, it will be shifted to the odd state. So, there will be a transition. So, with one input having even state, there will be a state transition from even to odd. So, this is a state transition occurs from 0 to 1 state. Now, similarly, if the present state is odd means the 1 encoded as 1 and 0 input has come, then again it will, because it will be in the same state, but output will be 1, and if it is a present state is odd and again 1 input arrives, then it will come back to the even state, and that means there will be a state transition, and that is a state transition from 1 to 0, 1 to 0. So, this is the state diagram of the FSM, the finite state machine. Now, if the machine just now we have designed, if it is implemented by a flip flop. So, what we have seen that if we see the state transition table, we see that if the present state, and say these are my if these are my inputs, see if these are my present state and input are taken as the input of the machines, then this 0 0 is output is 0, then 0 1 again that next state is 1 and output is 0, 1 0 the next state is 1 and output is 1, 1 1 is next state is 0 and output is 1. As I mentioned earlier that actually if we consider the present output, here it will be 1 and here it will be 1, but we are taking the output after one clock cycle, that is here after one clock cycle this is shifted like this, and that is why after one clock cycle the output is being shown at the output table. Now, if we see the next state, see 0 0 0, 0 1 1, 1 0 1, 1 1 0. So, this is nothing but the truth table of 2 input XOR. So, now this is my input and this is my present state. So, this is my this input is 1 and this present state that has come here. So, these are the 2 inputs of the XOR and this is my next state. So, it will be the truth table will be 0 0 0, 0 1 1, 1 0 1 and 1 1 will generate a 0 again. Now, another thing, say here what is the function of this D flip flop? See that this next state, that next state is 0 1 1 and the 1 0 1. As it is a D flip flop, we know that at when the clock is high, the D input will pass to the Q output. So, after one clock pass, this will be my output. So, this will be the output will be shown here, and this is the function of the, that means after one clock pass the outputs will be passed from here to here, and this is the design of the odd parity checker. Now, if we see the timing behavior, so input is, say I am taking that high clock pulse means 1, low is 0. So, if it is a bit stream 1, say 0 0, again 1 1 0 1 0 1 1 1 0, like that. So, that means the clock is 1 full clock pulse, it is 1. So, this is up to this it is 1. Similarly, here it is 0 0 1 1 0, here it is 1, like that. Now, when the clock is 1, see here input is 1, that means odd number of ones. So, output will be a high 1. Similarly, now next 0 has come, again 1 0 means then also it is a odd parity, means odd number of ones in the input bit stream. So, output is 1. Again next bit arrives or next input bit is 0. So, 1 0 0, again it is odd. So, again the parity bit is 1. Now, 1 arrives in the input bit. So, there are even number of ones. Now, there are 2 ones. So, it becomes the odd parity checker will generate a 0 output. So, here it will be a 0 output. Now, similarly, again if another one comes, then 3 ones. So, it will be a odd parity generator will give 1 output, next 0 again 1 output, next 1 means it becomes 1. So, what we are seeing the timing behavior, that with the clock pulses, that if odd number of ones are counted, then the output generated will be a 1, and if when it becomes even number of ones in the input bit stream, then 1 0 output will be generated. So, what will be the basic design approach? First, we should realize the statement of specification. That means, the problem statement should be specified clearly, that what machine or for what input, what output will be generated. Then develop an abstract specification of the finite state machine. Here abstract specification means that if we know that machine, last day we have defined that the output or the next state depends not only on the present input, but also on the previous state or the previous state and the time. So, we will be specifying depending on the problem statement that what will be the present state, what will be the next state, and what is the status of the output then. Then minimize the number of states, because always our aim is to design a compact machine or compact circuit or minimized circuit. So, if the number of states n number of states are needed, then at least we need log n number of flip flops. For this particular example, we have seen that for this odd parity checker, that we have two states, even and odd. Even and odd state. So, there are two states. So, I need only one bit to encode the states, one bit 0 or 1. Now, perform state assignment and then choose flip flop types to implement FSM state register. That means, we have read different type of flip flops, D, T, RS flip flop, JK flip flop, then which flip flop we have to choose to design that particular FSM and then implement the FSM. So, these are the basic design flow of a FSM design. Now, we take one very popular and very common example of the machine design, and that is called a vending machine FSM. Now, the first step is the problem specification. So, problem is that we have to construct or we have to design a circuit so that deliver a train ticket, that circuit will do this function, the deliver a train ticket after ₹3 is deposited as single coin slot and no change. That means, if we deposit 3 rupees by some coin, it will take, the machine will take only coins, then it will deliver it will produce a ticket, otherwise not, and there will be no change. So, step 1 was that realize the statement. Then this is the block diagram level of the circuit. So, see, I have this is my FSM that to be designed, and see, this is a coin sensor, means here I am putting or depositing the coin, to deposit the coin. See, there are two type of coins, two inputs I have taken, that N and D, and this is a reset line, the machine reset line. Machine has another input, clock, as already we have seen when we have learned the sequential machine design, that all the flip flops have two lines, one input is the clock, another the reset lines, that means where to start, for on which signal it should start. Then open means it generates a output, that means it will deliver a ticket. So, it will release or say deliver a ticket. And this is the overall block diagram, that means with the input, output and the machine itself. Now, we try to draw the state diagram or the abstract representation. So, what will be the typical input sequences? See, I start with a initial state or the starting state S0. This is my S0. Now, say I have two type of inputs I have considered, one is called N, one is D. Now, for this particular example, say D means 2 rupees coin and N means 1 rupees coin. We have not considered any 50 paise coin or 25 paise coin, only two input we have taken the 2 rupees. So, if now I deposit a 1 rupees coin, so it will proceed, because still or it forwards the step, because there are chances that another 2 rupees coin may be deposited or another 2 number of 1 rupees coin can be deposited. So, it proceeds further, that means is a state transition occurs from S0 to S1. Now, as already 1 N means 1 rupees coin, 1 has come. Now, there can be a 2 rupees coin, then 1 plus 2 3 rupees coin. So, it will generate a output, that means ticket will be delivered. So, this open means that ticket is delivered. Now, from S1 say 1 rupees coin is deposited. Now, if another 1 rupee is deposited, then it is 1 plus 1 and it goes to state S3. Now, if it is again 1, then actually 1 plus 1 plus 1 means 3. So, again it will generate a output, means a ticket will be delivered. Now, see at the state S3, the S3 state means already 2 rupees are deposited. Now, someone can put another 2 rupee, then it is 2 plus 2 means 4 rupees, which is greater than 3. So, again one ticket will be delivered, means one output. Similarly, if from the initial state, that means first someone puts 2 rupees instead of 1, then it can be two other state, either someone can put another 2 rupees, then it is 2 plus 2 4, which is greater than 3, and someone can put 1 rupees, then it is 2 plus 1 means 3. So, both the cases a ticket will be delivered in this case. So, in this case there are 5 situations or 5 cases can occur where this ticket can be delivered, and these are the different ways of depositing the coins so that I can get a train ticket by 3 rupees. So, these are the abstract representation of my problem. Now, see, I starts with this state S0. So, this is my, again this is after resetting, every time the machine should start from this S0 state. This is called the initial state or the starting state. So, every machine has some starting state or initial state, where resetting, after resetting the machine will reach. So, S0, S1, S2, S3, S4, S5, S6, S7, S8. So, there can be 9 states here. Now, first we see the state table. So, first is the what are the present states. So, present states can be that 0, 1, 2, 3, that means S0, S1, S2, S0, S1, S2, S3. See, S0, S1, S2 and S3. Only these are the intermediate states from where the input, with one input, that one ticket can be delivered, and all are output state. So, if it is a S0 state, already we have seen, I can give a 0 0, means nothing has been deposited, obviously next state is 0, output is no output, 0. Similarly, if it is 0 means S0 state, so if this is my actually S0 state, and this is that if D is no means D means 1, D means 2 rupees coin and N means 1 rupees coin. So, 1 rupee can be deposited, then the next state will be 1, because it state transitions occurs from S0 to S1, output is 1, because I did not get 3 rupees. Now, 2 rupees can be deposited, then the next state will be 2 and the output will be again 0. Now, 1 means in the S0 1 2 rupees and 1 rupee can be deposited, but I have taken not parallelly, I have not taken that 2 inputs can be fed. So, that is why it is next state is taken as any one and any output state, and the output is actually output should be 1 and that should be taken as this cross. Similarly, if it is a now S1. So, again already it is 1. So, 0 0 means next state remains in 1, output 0. If it is 0 1, that means I have given 1 rupees coin, next state becomes 2, output is 0. Then 1 0 coin. Now, I got already 1 was there and 2 rupees coin is there. So, 3. So, this means I got a next state 3. So, this will generate a output 1. Now, similarly when it is S2 means 1 2 rupee coin is there. So, 1 and 1 2 rupee both will give a output, and when it is in 3 rupee, obviously nothing, anything can be, already I have got 3 rupees coin. So, this is S2, S3 means this is 3 rupees coin. So, already always the output will be 1. Now, again by simple state minimization we can do that thing. See, earlier the initially we have kept 9 states S0, S1, S2, S3 and these are actually output states. So, now it is minimized. So, if it is a S0 state, means there are no coin deposited. This is that no coin deposited. Now, say 1 rupee has come. 1 rupee means it will go to S1. Now, if it is 2 rupee has come, then also, so this is 1 rupee has come, this is 2 rupee has come, then also it will be, it proceeds and it go to S2. Now, see, if in the S1 state, that means S1 means 1 rupees coin is there deposited, 1 rupees coin. Now, if someone puts 2 rupees coin, that means it is 3 rupee and it should give a ticket. So, it will produce a ticket, or that is the open or that is the output, whatever we can tell. Now, if here S1 another one has come, it will proceed. If here it is a 2 rupees coin, then any one will also reach S3 or any 2, that means 1 or 2, any input will make the 3 rupees deposited. If it is 3 rupees deposited, if it is 2, then already it was 2, now 2, so 4 rupees deposited. So, in each of the cases one ticket will be delivered. Now, see that earlier when we have initially from the problem statement, the state transition we have done, we used 9 states. Now, these 9 states have been reduced to 4 states only, and these 4 states, now if we do the state encoding, so we need 4, that means log, so ceiling of log 4 means 2 bits are needed to encode. So, for state encoding we need 2 bits. So, this 0, 1, 2, 3, that I can write 0, 0, 0, 1, 1, 0, 1, 1. This is called the state encoding. So, now we do the state encoding table. See, just now what I mentioned, that the present states are 0, 0. Then the inputs, that 1 rupee coin or 2 rupee coin, D means 2 rupees coin and N means 1 rupee coin. So, if it is present state is 0, 0, then if no coin has been deposited, again it remains in the same, output is 0. If it is 0 1 means only 1 rupee coin is there, next state is 0 1 means, so this is my S0, 0 1 means this is S1, this is S2 and this is S3. So, it goes to S1, S1 means only 1 rupees coin state. So, if we write the physical interpretation of the states, what we can tell that S0 is first is it is the initial state or starting state. So, each time after resetting it will start from S0. It is encoded as 0 0. The physical meaning, what is the meaning, that no coin is deposited. Similarly, if it is S1 means encoded as 0 1 and here 1 rupees coin is deposited. Now, if it is S2 then 10 rupees 2 is deposited as coin, and S3 means either 3 or 4 means at least rupees 3 is deposited. So, it will give a output. Means one ticket is output, means one ticket is delivered. So, if we see, this is my 0 0, that is my S0, 0 1, that is my S1, 1 0, that is my S2, and 1 1, that is my S3. So, these 4 states are there, and then the all possible inputs we have considered. With every initial state, or if the machine lies in that particular state, then if all possible inputs or in any of the inputs come, then what will be the next state and what will be the output that we have considered in the state encoding table. See, now again it becomes as a truth table, and which has some 3 inputs as if, means here the output depends on the present state as well as the present input. So, see that here D and N, that are the input, means that what coins are deposited, and here Q1 is the state or the present state. Again Q1 Q0, that is also present state. So, if we draw the Carnot map, that means Dn and Q0 Q1 are the, as if they are treated as the inputs, and it will generate a single output, then we will be getting this type of Carnot map realization from the previous table. See here that dn 0 0, q 0 q 1 is 0 0, then the output is 0. Similarly, if it is 0 1 and still the dn inputs are 0 0, then it will be 0. In that way we can do that thing. So, now after minimization, Carnot map minimization, if we complete the circuit, then it will be like that. Say for each output of the AND gate there are q and n. Now, after minimization we get that d1 is q1 plus d plus q0 n. So, if we realize that thing, then first is this is a q1 and q0. So, this is my q1, this is my say q0. Now, again this q1, actually that should be d1 is q1 plus d plus q0 n. So, here there will be this OR gate has one input q1, second input is d and it will be q0 n. So, this is q0, this is n. So, it will generate this d1 input. So, if I now put one d flip flop here, so this is my as if d input and this is my q input. So, this is my clock and this is reset. Now, what will be d0? d0 is nq0 plus q0n plus q1n plus q1d. So, there are four AND gate. So, first we realize that nq0, so this will be n, this will be q0, similarly this will be q0, this will be n, this is q1, this is n and this is q1d. So, this will be the q0 and similarly if I put a d flip flop at this input, then this will be the d output and this will be the q0. So, as if this is d0, this is d1, this is q bar, this is reset, this is clock. So, see 4 AND gates or 5 AND gates and 2 OR gate and another 1 AND gate at the output. So, total 8 gates are needed for the design, among which 5 are 5 AND, 2 OR, and actually we can tell 6 and 1 AND at the output. So, these 8 gates are needed for this particular design. So, now we have got this is one vending machine design, just now what we considered. Now, we define two general machines or conventional machines. Normally, the overall machines or any type of machines that is classified as Moore machine and the Milli machine. Now, what do we mean by Moore and Milli, that we define now. Now, again the general machine, as we have defined, that outputs depend only on, for the Moore machine, the output depend only on the current state, say only on the current state, and the outputs change synchronously with state changes. That means, whenever a state changes, because the output depends only on the current state, so the output will change. So, if we see the, already we have seen that this is a combination circuit, and here it was for the machine, it was some memory, but here it does not depend on the previous state. So, it is the current state. So, the input here comes, these are my inputs, and this is a register, that means the present output of the combination logics are stored, and again these outputs are fed back to the combination block as the remaining inputs, and the output depends on the current state. So, this is the combination logic for outputs. This is combination logic for output. So, that Moore machine depends only on the current state. Now, if it is a Milli machine, the outputs depend on current state as well as the present inputs. So, this is the difference, that for Milli machine, that current state and present input, and the input change causes an immediate output change. That means, the output change occurs only when the input changes. So, what will be the general circuitry? That these are the present inputs, present outputs, and as this depends on the current states and present inputs. So, some of the output bits, it goes to a register, this clock, or a, we have seen this is actually a set of flip flops, and then the output is fed back as the remaining inputs of the combination logic circuits. So, this is the general circuitry, that one combinational logic and the memory flip flops or the memory elements flip flops, or I can tell memory elements are there, some of the inputs, some of the outputs, and some of the outputs are fed back, and this is the circuitry. So, this is my Mealy machine. So, now we see the FSM word problem. So, a problem defined in English is mapped to formal specification. Say it is a pattern recognizer. Now, pattern recognizer means, that means one machine we have to construct where a particular pattern is, if it is fed, then only one output will be generated, otherwise always the machine will generate a 0 output. So, we define a pattern recognizer is a sequential system whose binary output at time t corresponds to the particular pattern predefined recognized by the system. Now, a finite string recognizer has one input and one output. The output is asserted whenever the input sequence, say 0 1 0, has been observed. That means, if 1 0 1 0 arrives, then only it generates the output, and as long as the sequence 1 0 0 has never been seen. That means, if 1 1 0 0 is reached, then this logic is not valid so far, or this logic is not valid anymore. That means, that it will stop generating that output for this condition, that is 0 1 0 arrives. So, step 1 is that understanding the problem statement. Say input. Now, we see example. See 1 0 has come, output 0, 0 has come, output 0, 1 has come, output 0. Now, 1 0 has come. So, see this is a 0 1 0 and the condition is satisfied. So, one output is generated. This is one output. Similarly, 1 0 1. So, it is now 1 0 1 0 is arrived. So, this is again 1 1. That means, this is a 0 1 0, this is a 0 1 0, this is a 0 1 0. Now, see 1 1 0 0 has arrived. So, this is a 1 0 0, that means terminating, or the condition which is not valid. Okay. So, it will be now, see now 1 0 1 0 has come, but output is 0, but this output is 0. So, this is the problem statement written. Now, if we draw the state diagrams for the string, that must be recognized. So, just now the what example we have seen, that this is a reset initial state, this is the initial state, that reset, and now that see if it is 0 comes, then it is S1. Now, again another 0 has come, so again it is a S2. If it is another 0, then again it will be in the S3 state. Now, if 1 comes, then it obviously it will be a different state, because from the initial state, if 0 comes, it will go to one state, it will be in one state. Then again some 1 has come, now again. So, this is if it is a 1 0, Now, it can be 1 0 0 or 1 0 1. So, this type of different type of state transitions will occur. Now, exit condition from state S3. So, the exit conditions from state S3 have recognized that 0 1 0, if next input is 0, then have 0 1 0 occurs. Now, in next input is 1, then have 0 1 0 1. So, again that what we have done, that we are mainly we want to construct a pattern recognizer, and the design principle, what the basic design approach what we have seen, that first we have to realize the statement of specification. So, that part we have done, that if that 0 1 0 comes, then only it will generate output, otherwise not. But if it is valid until 1 0 0 pattern arrives. If 1 0 0 arrives, then this condition is not valid, it is not valid. That means, even after 1 0 0, even that 0 1 0 comes, then the output will not be 1. Now, that part we have read. Now, develop an abstract specification of the FSM. So, what we are doing, actually the second step. So, this step we have done for the pattern recognizer. Now, the second step means, now there how many states are possible, because now we want to that if this is the present state, what we want, that if a input comes, then what will be the next state? What will be the next state? So, for all the conditions, for all the cases of this pattern recognizer, that we have to design, and then that time what will be the output, whether the output will be 0 or output will be 1. So, next step we will be starting from the step 2. So, we have defined the problem, and next step we will be doing the abstract specification, that is the state table, then the state encoding, and then how the machine will be designed. So, we will continue there, we will be finishing here.